Hey, welcome to chemistry. This is Miss Gray and we're in Unit 6. Today we're going to look at empirical formulas and molecular formulas. I've got an ionic compound to show you, sodium and chlorine together that make sodium chloride. This is what we call an empirical formula when we would have one sodium for every chlorine. Now let's look at a molecule. In this molecule, you'll see each particle of hydrogen peroxide has 2 atoms of oxygen and 2 atoms of hydrogen that are covalently bonded together. But what this means for us is that the particles are not exactly the same type of particles. See, ionic compounds are made of ions, right? And the ions arrange themselves in such a way that they reduce the repulsive forces between like charges, so these chlorines stay as far apart as possible, and then they increase the attractive force between the positive and the negative. So we keep our positives far from each other, but we keep them surrounded by negative charges all the way around. So we set up a mole ratio to describe how many chlorines to how many sodiums. But in a covalent compound, these particles are not ions, they're molecules. And they're sharing electrons, and so the particle actually exists in this form, where there's 2 oxygens that are bonded to 2 hydrogens, and they're stuck together, and they hang out together, and they stay like that. So ionic compounds are always expressed as the simplest whole number ratios, or formula units. But covalent compounds can be either molecular formulas, or they could be empirical formulas. And so if I ask you for the molecular formula, you need to know more about it than just the empirical formula alone. Because look, this is reducible. H2O2 could reduce to the form simply H and O. So that's what we're going to be working on today. So first of all, let's just decide what is the empirical formula for any of these compounds. So by empirical formula, we mean in simplest terms. So we have to reduce it if it's not in simplest terms. Propene has the molecular formula C3H6. Notice they're both divisible by 3. So I'm going to divide everything inside here by 3 and I get CH2. There's the empirical formula for propene. Now let's do ethene. What's the common term here? Right, they're both divisible by 2. So CH is a great empirical formula for ethene. Now look at glucose. All of these subscripts are divisible by what number? Right, by 6. So we get CH2O, which is a typical formula for sugars. And then octane is, let's see, that's divisible by 2. Is there anything higher than that that'll work? I guess not. So we get C4H7. Right? So that's now in its simplest terms. So we've turned all of our molecular formulas into empirical formulas by reducing them so that we can't go down anymore. All right, the next step is simply to identify which of these are empirical formulas, which of these are molecular formulas, and which ones do you think could be both. So for example, H2O cannot be reduced any farther. So it's definitely an empirical formula. But does it describe the makeup of the molecule itself? A water molecule is made of 1 atom of oxygen with 2 atoms of hydrogen. And so this describes the actual molecule as well. So that's a molecular formula and an empirical formula. So number 1 is both. Okay, number 2, C4H10 can be reduced. So that must be a molecular formula, not an empirical formula. How about CH? That's definitely reduced in its simplest terms, and so that's going to be an empirical formula. Now, could we have a molecule where carbon is bonded to only just 1 hydrogen? Would that work? Not when we understand that carbon has 4 valence electrons, right? What do we do with the rest of these things? And so that can't be a molecular formula, but it could be an empirical formula. Okay, how about NaCl? It's in simplest terms, so it's an empirical formula, but you know what? It's ionic, and since it's ionic, it won't have a molecular formula. So it's not molecular, it's only empirical. That's how we decide. Now here's our steps to calculate the empirical formula, because I'm not always going to tell you what the empirical formula is, but you'll have the information you need to figure it out. Maybe it comes from percent composition, like what we were doing the last time. What is the empirical formula of a compound that is 25.9% nitrogen and 74.1% oxygen? Well, let's work this out. The first thing that we're going to do is we'll assume that the number of grams that's given to us, the first step is that we'll assume the percent given to us is equal to the number of grams. So we're going to take the percent that is nitrogen, 25.9, and change percent to grams. So this sign becomes a little g, and then 74.1% becomes 74.1 grams of oxygen. Our second step is the typical step in a problem. Go to moles. Let's convert the number of grams to moles using the gram atomic mass for nitrogen and for oxygen. So here's how we would do it for nitrogen. 25.9 grams of nitrogen goes into our first step in the T table. That comes from the percent composition here. And then 14 grams per mole for nitrogen is from your periodic table. I want to put it in here so that grams can cancel, right? So if I have grams on the top, grams has to go on the bottom in the next step. So that gives me 1.85 moles of nitrogen. Now we're going to do the same thing for oxygen. Oops, except I don't think I have that T table. Let's do it here. 74.1 grams of oxygen. And then look on your periodic table. 1 mole of oxygen has a mass of 16 grams. So now we're going to need a calculator. Okay, 74.1 divided by, where's my divide? There it is, divided by 16. 4.63. Okay, so what is that? 4.63 moles of oxygen. All right, well now our third step is going to do something with the moles. Divide by the lowest number of moles to obtain the simplest whole number ratio. So the lowest number was nitrogen, 1.85. So when we divide 1.85 by 1.85, that's equal to 1. Then we take 4.63 for oxygen and we'll divide it by the same number. That way we can get to the simplest whole number ratio. And I got 2.5 moles of oxygen for every 1 mole of nitrogen. That's not whole numbers though, is it? So we have a fourth step. If necessary, if you're getting numbers here that are not whole numbers, then you need to multiply by a whole number to obtain a whole number ratio. I know that step sounds kind of confusing, right? But how do we get rid of 2 1/2? How do we get rid of this denominator here? You can get rid of a denominator if you multiply by that same denominator. So we're going to take 2.5 times 2. If we had 1/3, then that would have the decimal point 3. We would multiply by 3. Well, what if we had 1/4? That's the decimal point 25, and we would have to multiply by 4 so that we can get to a whole number, right? And then the last one, we could do 1/5. What do we multiply that one by? 1/5 is multiplied by is the decimal point 2, and we multiply by 5. Yep, so you're already headed the right direction, huh? Okay, well let's see that math here. First I take my nitrogen moles and multiply them by 2. So now I have 2 moles of nitrogen. Then I'm going to multiply oxygen by the same amount. So 2.5 times, whoops, missed a number, 2.5 times 2 is equal to 5 moles of oxygen. Then we write the chemical formula by putting those numbers in. So 2 moles of nitrogen is N2. 5 moles of oxygen is O5. So we would name this dinitrogen pentoxide. There you have it. That's how we determine the empirical formula for any compound. Sometimes you'll already be given the number of grams, then you don't have to bother changing percent to grams. Just use the grams that they give you. Okay, now let me show you what to do for a molecular formula. In this problem it says the empirical formula of a compound is CH2. If its molecular mass is 70 grams per mole, what is its molecular formula? So first of all, we need to determine the mass of the empirical formula. We call it the empirical formula mass. So we take carbon and 2 hydrogens, and we get 14.03 for the empirical formula mass. So if this CH2 is all there was to that particle, it would only weigh 14 grams per mole. But it doesn't. The molecular mass is 70 grams per mole. So now our next step is to take the molar mass divided by the empirical formula mass. So we do 70 grams per mole divided by 14 grams per mole. So let's get our calculator and let's do the math. 70 divided by 14. And that's equal to 5. So that means I have a particle that is 5 times as big as what the empirical formula mass says. So what I do then is I take my empirical formula and I multiply everything inside there by 5 because I need something 5 times bigger than that. So our true formula for this molecule is C5H10. And that's how we do molecular formulas. That's all there is to it. Great, so I will see you guys in class. Work hard and study.